Hi everybody, my name is Oscar Rojas. I'm a PhD student working with Dr. Hans Stein. And today, I will talk about the use of feed technology to improve the nutritional value of feed ingredients fed to pigs. This is the take-home message of my presentation. The first point is that reduction of particle size of corn increase energy and starch digestibility. The second point is that it is possible to reduce fat addition in diets without reducing growth performance or carcass characteristics. The third point is that energy utilization may be improved by pelleting, extrusion, or the combination of both systems in diets fed to pigs. And the last point in our presentation today is that the use of cellulase may increase the energy value of DDGS. This is the outline of this podcast. I will start with a brief introduction about some ingredients that are commonly used in diets fed to pigs, and then we also review some types of feed processing. Then we will move on to a summary of 7 experiments that are related to energy and nutrient digestibility and growth performance. And this part will be divided in 3 sections. The first section is related to corn particle size. The second section is related to the use of different technologies, either extrusion, pelleting, or a combination of both systems in diets with different levels of fiber. And the third section will be related to the use of chemicals, enzymes, or extrusion technology to improve the nutritional value of DDGS. And then we'll finish this presentation with some general conclusions. In this slide, we have our pig and this is our system. In all the systems, we have an input and an output. As an input, we have our diets, and as a swine nutritionist, we can control our input, so we can decide what type of ingredients we want to include in our diets and at which concentrations they are going to be included. And also we have our output, that in this case are the feces. And sometimes we have the opportunity to use different feed technologies, such as grinding, extrusion, pelleting, chemicals, or enzymes, either by itself or in combination to our diets. And if we fail to use any of those technologies, or if we fail to include the right concentration of ingredients in our diets, we are gonna increase the excretion of nutrients in our system, in this case the feces. And this means that we are gonna lose money, and also we are gonna contaminate the environment with those nutrients that are excreted. In this slide, we observe the neutral detergent fiber in different ingredients that are used in diets fed to pigs. We have corn, soybean meal, DDGS, and soybean hulls. We observe here that when we include corn and soybean meal in our diets, our NDF concentration range between 8 and 10%. However, when we move to an alternative ingredient such as DDGS and soybean hulls, we increase the concentration of fiber in our diets. This means that as we increase the concentration of fiber in our diets, energy and amino acid digestibility is reduced, and therefore this generates an opportunity for us to use different technologies to increase the nutritional value of that fiber. When we use different feed technologies, we have some advantages. Some of them are increases availability of nutrients, decreases excretion of nutrients. We may observe an increase in performance. We also may observe an increase in gelatinization of the starch, and also we can observe an improvement in feed handling. We also may observe some disadvantage when we decide to process our diet. The first one is that processing will add cost to our diets. Excess of heat will reduce the digestibility and the concentration of lysine. You could also get retrogradation of starch, and this means that we generate resistant starch, which will decrease the digestibility of energy. So the overall objective of this presentation is to determine the effect of different processing techniques on energy and nutrient digestibility of diets and ingredients fed to pigs. Let's start with the first part of this podcast that is related with corn particle size. The objective of the first 2 experiments was to determine the concentration of DE and ME and the digestibility of phosphorus, amino acids, and starch in corn grain that was ground to different particle sizes and fed to growing pigs. It has been recommended that corn may be ground to a particle size between 600 and 650 microns. This could be accomplished by the use of either roller mills and hammer mills. However, now the industry is trying to move to a combination of both systems, trying to increase grinding efficiency and to reduce variability. However, there are some problems related when we try to reduce the particle size. The first problem that we may observe is that as we try to reduce the particle size of corn, there is an increase in electricity costs at the feed mill, which will increase the energy costs. Also, as we reduce the particle size, we may observe a reduction in flowability. But if we decide to pellet our diets, this is not going to be the case. And also, it has been reported that as we reduce the particle size of corn, we may observe some ulcers in the stomachs of those pigs. So we start with a single batch of corn. This corn was ground using a roller mill to a mean particle size of 2000 microns. Then we use hammer mills with different screens to obtain 4 different particle sizes of corn: 865 microns, 677 microns, 485 microns, and 339 microns. In this slide, we observe the apparent ideal digestibility of starch, and we observe here that as we reduce the particle size of corn from 865 microns to 339 microns, apparent ideal digestibility increased linearly. And when we look at apparent total tract digestibility of gross energy, we observe the same pattern as we observe for the apparent ideal digestibility of starch. As we reduce the particle size of corn, we observe that the digestibility of gross energy increases. Here, we observe the concentration of Me in dry matter bases, and we observe also that as we reduce the particle size, the concentration of Me increases. And the reason of this is that as we increase the digestibility of starch, then we increase the concentration of Me as we reduce the particle size of corn. And it's important to mention that reduction of particle size of corn did not have an effect on phosphorus and amino acid digestibility. So what are the implications of these two experiments? Because of the increased Me in corn ground to a smaller particle size, it may be possible to reduce fat addition in diets if corn is ground to a smaller particle size. So based in our previous result, we wanted to test the hypothesis that the addition of dietary lipids can be reduced as corn particle size is reduced without affecting growth performance or carcass characteristics. For this experiment, we used 72 pigs with initial body weight of 32.0 kilograms plus or minus 1.58 kilograms. We had 36 gills and 36 barrows that were housed individually. We have 18 pigs per treatment, and this experiment was designed to contain 3 phases. The first phase was between 32 and 62 kilograms, the second phase was between 62 and 94 kilograms, and the last phase was between 94 to 129 kilograms. In this slide, we observe how we formulate those diets. As I mentioned before, we have 3 phases: phase 1, phase 2, and phase 3. For phase 1 diets, as we reduce the particle size of corn from 865 microns to 339 microns, we reduce the concentration of oil from 3.6 to 2.0. And the reason of this was to maintain the concentration of Me among diets, in this case 3,396 kilocalories per kilogram. And we used the same approach to formulate phase 2 and phase 3 diets. Here we observe the overall growth performance for this experiment. We have average daily gain, average daily feed intake, and gain to feed ratio. And we observe here that reduction of particle size did not affect average daily gain or average daily feed intake. However, as you observe here, as we reduce the particle size of corn, gain to feed ratio is reduced. Here, we observe the whole carcass weight in kilograms. We observe that as we reduce the particle size of corn, whole carcass weight is not affected. However, when we calculate dressing in percentage, we observe that as we reduce the particle size of corn, dressing percentage increase linearly. And the reason of this is that pigs that were fed a diet containing corn ground to 865 microns, the GI tract of those pigs were heavier compared with pigs that were fed a diet containing corn that was ground to 339 microns. And if you remember, I mentioned before that as we reduce the particle size of corn, we observe that gain to feed decreased linearly. However, we recalculate that gain to feed ratio, but now based on whole carcass weight, and we observe here that reduction of particle size did not affect gain to feed among treatments. In this slide, you can see the concentration of short-chain fatty acids in cecal contents. We have acetate, propionate, and butyrate, and you observe that as we reduce the particle size of corn, we reduce the concentration of each of those short-chain fatty acids. And the reason of this is that as we reduce the particle size of corn, there are less nutrients coming into the large intestine, and therefore there is less fermentation. We also measure pH in different contents, ileal content, cecum content, and colon content. And we observe here that there is a greater pH as we reduce the particle size of corn in cecum contents and colon contents. This indicates that as we reduce the particle size, there is less fermentation, and therefore we observe a greater pH in those samples. We also were aware that as we reduce the particle size, we may observe some lesions in the stomachs of the pigs. In this slide, we observe the different sections of stomachs of the pig. We have the esophageal region, cardiac region, fundic region, and pyloric region. And as you observe, the cardiac region, fundic region, and pyloric region have a mucus, and that mucus protects those sections of the stomach against the hydrochloric acid. However, this is not the case for esophageal region, and that's why, as we reduce the particle size, it has been proposed that that region is affected. In this slide, we observe the frequency of lesions in the esophageal region in those stomachs. We consider those stomachs normal in orange, blue as a minor lesions, medium, green, and red major lesions. For example, for the diet containing corn ground to 865 microns, we observed that 50% of those stomachs were considered normal, and 20% of those stomachs had some level of lesions, minor lesions, and 20% were considered medium lesions. However, as we reduce the particle size of corn, we observe, for example, in the case of 339 microns, that none of those stomachs were considered normal, and in fact, almost 40% of those stomachs had minor lesions, 20% were considered medium lesions, and almost 35% of those stomachs had major lesions. It's important to mention that none of those stomachs had ulcers, they just have some level of parakeratinization. In this slide, we can see the esophageal lesion score. 0 means that no lesions were observed, and 10 indicates ulcers. We observe here that as we reduce the particle size of corn, the lesion score increased linearly. So the implication of these growth performance experiments are that it is possible to reduce fat addition in diets if corn is ground to a smaller particle size without affecting growth performance or carcass characteristics. And also, we need to be aware that as we reduce the particle size, we may observe some level of lesions in the stomachs, and also we may observe problems with diet flowability in our feeders. Once we conduct the grow and finish experiment, we wanted to test if we may observe the similar response using weanling pigs. So we wanted to test the hypothesis that caloric utilization of corn fed to weanling pigs is increased if particle size of corn is reduced. In this slide, we observe the soybean oil concentration in diets for two different experiments. For the first experiment, we wanted to maintain constant the concentration of corn and the concentration of soybean oil among diets, and that's why we have different values for ME concentration. And that's why we observe that as we reduce the particle size of corn, ME is increased. However, for experiment 2, we wanted to maintain constant the concentration of ME in our diets, in this case 3000 to 3413 kilocalories per kilogram, and the way how we accomplished this was using the same approach that we used for the grow and finishing experiment. So what we did, we reduced the concentration of soybean oil as we reduced the particle size of corn in our diets. Here we observe the group performance data for experiment number 1, and we observe that as we reduce the particle size, gain to feed ratio increased linearly. And the reason of this is that average daily feed intake is reduced. And what this means is that pigs that were fed a diet containing corn ground to a 339 microns, they don't need to eat as much as pigs fed diet containing corn ground to 165 microns, because those pigs will get more energy in that corn that was ground to a smaller particle size. For the second experiment, we wanted to maintain the energy constant, and by doing this, we were assuming that we will obtain similar gain to feed ratio among treatments. However, as you can see, this was not the case. We observed that as we reduce the particle size, there is a linear increase in gain to feed, and we were not expecting this, because we formulate those diets to have the same concentration of ME among diets by reducing the concentration of soybean oil as we reduce the particle size of corn. And we believe that the reason of this observation is that those younger pigs were not able to absorb the fat coming from the soybean oil, and that's why those pigs were not able to maintain similar values of gain to feed. We also measured pH in colon content for those two experiments, and we observed the same pattern as we observed for the grow and finishing experiment. We observed that as we reduce the particle size of corn, there is a linear increase in the pH, indicating that there is less fermentation as we reduce the particle size of corn. So the implications for those two experiments are that if diets contain corn ground to a particle size of 339 microns rather than a greater particle size, gain to feed of pig is improved, and also inclusion of dietary fat may be reduced if corn is ground to a finer particle size. The general conclusion for the first part of this podcast is that there is an increase in apparent lineal digestibility of starch and the concentration of DE and ME as we reduce the particle size of corn, and also it is possible to reduce the addition of lipids in the diets if corn is finely ground without affecting growth performance or carcass characteristics. So now let's move on to the second section of this podcast, looking at the effect of extrusion and pelleting, or the combination of both systems, on energy and nutrient digestibility in diets with different levels of fibers fed to pigs. The objective of this experiment was to test the hypothesis that pelleting and extrusion of diets, either alone or in combination, will improve the nutrient and energy digestibility, and this response is greater in high fiber diets than in low fiber diets. For this experiment, we have three different levels of fiber: low level, medium level, and high level. In the case of low level of fiber, this diet was a combination between corn and soybean meal. In the case of medium level of fiber, we include 25% of DDGS, and in the case of high fiber diets, we include corn, soybean meal, 25% of DDGS, and on top of that, we add 20% of soybean hulls. So now let's see how we process those diets. We have 4 different types of processing. If we take, for example, the low level of fiber, corn soybean meal diet, we mix that diet and we call that the meal diet. Also, if we pellet that diet, we call it the pelleted diet. We also extrude the corn soybean meal diet, and we call that the extruded diet. And if we first extruded and then pelleted, we call that our last treatment, extruded and pellet diet. Pellet of the diet was at 85 degrees, and the extrusion of the diet was at 115 degrees Celsius. Here we observe the apparent linear digestibility of a starch, and here we are looking at the effect of processing. As we process the meal diet either with pelleting, extrusion, or a combination of both systems, we observe that the digestibility is increased compared with the meal diet. Now, when we look at the apparent linear digestibility of lysine, we observe that digestibility of lysine is improved in pellet diets, extruded diets, or the combination of both systems compared with the meal diet. However, the extruded and pellet diet, in the case for digestibility of lysine, was not different for extruded or the pellet diet. Now, when we look at the apparent linear digestibility of threonine, we observe the same pattern as the previous slide. As we process the meal diet, either with pelleting, extrusion, or the combination of both systems, we observe that the digestibility of threonine is improved compared with the meal diet. And it's important to mention that for all the indispensable amino acids, the apparent linear digestibility was greater for pellet, extruded, or extruded and pelleted diets than for the meal diets. Here we are looking at the apparent total tract digestibility of gross energy. We observe here that the pellet diet and the extruded and pellet diet have greater digestibility compared with the meal diet. However, they were not different than the extruded diet. In this slide, we observe the Me concentration on dry matter bases, and in this case, we observe an interaction between fiber and the type of process. We have in the blue bars low level of fiber, orange bar the medium level of fiber, and the red bar represents high level of fiber. And we observe, first of all, that as we increase the concentration of fiber in the diets, there is a reduction in the concentration of Me in our diets. We also observe that as we process the diet, either with pelleting, extrusion, or the combination of both systems, the concentration of Me increased compared with the meal diet for low and high fiber diets, but this was not the case for diets containing medium level of fiber. And also, we observe here that the increase in Me concentration was greater in high fiber diets than in low fiber diets. So the implication of these experiments is that ileal digestibility of amino acids and starch is improved by pelleting, extrusion, or the combination of both technologies, and also that extrusion improves energy values to a greater extent in high fiber diets than in low fiber diets. And our last section of this podcast is the effects of chemicals, physical, or enzymatic treatments on the concentration of Me and the digestibility of energy in DDGS fed to pigs. The objective of this experiment was to determine the effects of physical, chemical, and enzymatic treatments on the concentration of Me in DDGS. For this experiment, we start with a batch of DDGS, and this batch was divided in 6 sub-batches. The first batch was called untreated DDGS, the second batch was extruded, the next 2 batches were treated with either calcium oxide or sodium hydroxide, and the last 2 batches of DDGS were treated with the addition of cellulase or hemicellulase. Here we observe the concentration of Me in dry matter bases, and we observe here that when we treat DDGS either with extrusion, sodium hydroxide, or hemicellulase, we did not change the concentration of Me compared with the untreated DDGS. However, when we treat the DDGS sample with cellulase enzyme, we observe that the concentration of Me increased compared with the untreated DDGS. So the conclusion for this experiment is that cellulase treatment was effective in improving the concentration of Me in DDGS, and hemicellulase, extrusion, sodium hydroxide, or calcium oxide treatments of DDGS did not consistently improve the concentration of Me or the apparent total digestibility or gross energy in DDGS. So the overall conclusion for this experiment is that the use of fine grinding, enzyme addition, extrusion, or pelleting may positively influence the energy and nutrient digestibility in ingredients and diets fed to pigs. So once again, to remind you the 4 important points of this presentation: reduction of particle size of corn, increased energy and starch digestibility. It is possible to reduce fat addition in diets without reducing growth performance. Energy utilization may be improved by pelleting, extrusion, or the combination of pelleting and extrusion in diets fed to pigs, and the use of cellulase may increase the energy value of DDGS. Thank you for your attention.